Henry Van Gameren. I'm going to be your moderator for today, and today's is part one of four for the series, depending on how many questions we have. And I'm sure there's going to be a lot of questions coming from the session today, and we'll try to get to everybody. But unfortunately, because there are so many people joining us, so maybe some of these questions are going to be shared with you through the email following this session. So what are we going to cover today? Essentially, today's session, we're going to be covering homogeneous greenhouse climate through smart ventilation. And we have four major points. How do temperature differences occur in the greenhouse? What are the effects of leeward and windward ventilation separately? What are the benefits of using both leeward and windward sides simultaneously? And then lastly, configuration options in the Priva computer. So the first 3 points are going to be presented by Mr. Jan Voogd, and the last point will be presented by Mr. Hein Jaspersen. Our presenters today, as I just explained, Jan and Hein, they're waiting in the background here, ready to present. So I'm going to introduce you to Jan. We're going to start off with his first slide. Jan, if I could ask you to turn your camera and microphone on, and we'll get you on the screen here.
Okay. Can you hear me, Henry?
You're loud and clear, and we can see you. Thank you, Jan.
Thank you. Well, do you want me to start already?
Yeah, let's. I think we could. I think we can get going. I think everybody's settled in.
Okay, well, let me start with wishing you good morning, all of you. And Henry, thank you so much for your introduction and, of course, for having me in this Priva webinar. It is an absolute pleasure and privilege to be here together with the Priva team and to have the opportunity to present some of the principles of the plant empowerment cultivation concept to help you improve your climate control. Today, we will focus on realizing a more homogeneous climate, which means smaller differences in temperature, humidity, and also CO2 concentration across the greenhouse. And well, talking about homogeneous climate, of course, we first have to look at what if the greenhouse climate is not homogeneous. And I think that every grower will recognize the issues that may occur if the climate is not homogeneous. And we can have an uneven crop growth and development. We have risk of diseases and pests, and that all ends in loss of production and quality. Moreover, how can we possibly optimize the climate when there are cold and hot spots in the greenhouse? In this plot, in the slide, you can see the ground plan of a greenhouse that presents the temperature distribution across the greenhouse in different colors. The legend specifies the range of temperatures and colors. And as you can see, dark blue is a low temperature and red is a high temperature. And well, if we examine this spot, you can see there is a lot of cold and hot spots inside. And then the next question is how to realize a homogeneous climate. And then we have to look into what causes these temperature differences, how can we analyze and monitor these, and of course also how can we prevent these. And I will try to explain this briefly in the next couple of slides. Well, we have two main causes of temperature differences. The one is the thermal vortex, and the other is the Venturi effect. To start with the thermal vortex. Maybe not everyone knows this name, but after all, what's in a name? Let me explain this with the help of this figure. It shows a cross-section of a greenhouse at one side of the main path. We see the greenhouse cover that has a slope towards the side wall, of course, to ensure the rainwater in the gutter flows to the right. And when you grow on slabs, they will also have a slope to make the drainage water flow to the right as well. And we see in this picture there is a screen that is closed, but it has also gaps, maybe for temperature, maybe for humidity. But what will happen now? What will happen now is that warm air in under the screen will seek the highest point. So it will move to the left and then escape through the gaps. And there, above the screen, it will hit the greenhouse roof that is much colder most of the time. And the air will cool down, it gets heavier, and it will also follow the slope downwards to the side wall, getting colder and colder. And then when it hits the side wall, it will enter the greenhouse again through the gaps. And this makes the air circulating in this direction. And that's what we call thermal vortex. And as a result of this, you see that the temperature near the sidewall is much lower than in the midst of the greenhouse. And in practice, this can be easily 5 degrees or more. And you can also imagine that when this phenomenon has started, it is not so easy to stop it again because it has a self-maintaining character. And moreover, we have to be aware of the weight of this circulating mass of air. 1 cubic meter weighs about 1.2 kilograms. And that means that the weight of the air in one lane in the greenhouse, a large greenhouse, can weigh multiple thousands of kilos, multiple tons. And one can imagine that this circulating air mass cannot be stopped so easily. And as a result, there is a huge temperature difference between the midst of the greenhouse and the side walls. Well, secondly, we will look to the effects of wind and the opening of the vents. This is in the lower figure. This also shows a cross-section of a greenhouse, and the wind is blowing from the right. And the vents are opened, like in practice most of the time, at the lee side. The Venturi effect states that because of the speed of the wind on the right side, the dynamic air pressure is higher and the static air pressure is lower than inside the greenhouse. And on the left side of the greenhouse, where the wind speed has slowed down, the dynamic pressure is lower and the static pressure is less lower than in the greenhouse. And these pressure differences above the greenhouse causes warm air to escape here and cold air to enter the greenhouse here. And then you see that there occurs a temperature difference between the left side and the right side of the greenhouse. So that is the Venturi effect. And in practice, these two effects can occur separately or simultaneously, and they have the thermal vortex depends on temperature differences inside and outside, while the Venturi effect depends on wind speed and of course also the wind direction. And that means that these two phenomena can reinforce each other or they can counteract each other. But as a result, the climate is never homogeneous. Well, how can we monitor and analyze air movement and temperature differences? Smoke tests are a really fine instrument to visualize air movement. And I have a lot of experience with smoke tests, and I'm always surprised by the movement of the air. Seldom is what you expect, and it's very instructive to do that. Temperature differences can be visualized by a network, by an array of wireless sensors distributed across the greenhouse. And then you can make these plots. And it is also very instructive to make a time lapse of these plots. When you make a snapshot for every 5 minutes, for example, and you play them like a slow movie, it's very interesting to see how and when cold and hot spots occur and how they move across the greenhouse. You can also use multiple aspirator boxes, horizontal or vertical distributed across the greenhouse, and aspirator boxes above the screen are also very useful. These are extremely useful to visualize the effect of gaps in the screen. Well, I can only address this briefly in this webinar. So I like to refer to our book on plant empowerment basic principles, where you can find much more detailed information in chapters 4 and 8, and especially in chapter 10.1, we included a roadmap where you can see how you can step by step manage these temperature differences. I noticed that my microphone was switched off. Henry, can you help me out? Is that for a long time already? Sorry.
No, no short time.
Thank you, Hein. There was no problem. Well, where is my presentation? Now something went wrong, I think. Well, I seem to mess around a bit with my mouth. Excuses for that. And I'll try to go back to where I was. These are the 5 basic principles to improve the climate. And I will shortly address this. Well, principle 1 is prevent undesired openings. And this is a very simple principle. When hot air escapes through the one opening, always cold air must come in through another opening. And
Jan,
examples of these.
Jan, you just need to go to the, you need to take over um, the presentation and then move to the slide that you're on.
I see. Yeah. Is this the slide of principle one?
Principle one, yes.
Sorry for the distraction. Well, I'll start again to make sure that it's clear for everybody. There's a simple principle that if you have an opening in a greenhouse and warm air escapes through the one opening, cold air must come in through another opening. And examples of undesired openings are broken panes, of course, but also screen gaps, open doors, etc. So this has to be avoided at all times. Principle 2 is prevent cold fall by smart screening. And that I already mentioned, if you have gaps in the screen, warm air will go up at one spot and then always cold air will come down in another spot. So that's my statement. The best gap is no gap. Principle 3 is about preventing thermal vortex. And when we look at this picture again, you see that the, the problem of a thermal vortex is that warm air goes up and cold air comes down. So the best way to prevent thermal vortex is block vertical airflow. So by closing your screen for 100% and leaving no gaps, and of course even better is to have double screens. Well, in case you have no screens closed, so during the daytime, it may help to have a so-called apex seals, and they, with apex seals or vertical screens, help to divide the long lanes in a greenhouse in multiple sections, so the temperature differences will be less. In this example, you see the total length of the path is divided in 3 departments, and you can't avoid, or you can't have a solution for the complete solution for the occurrence of thermal vortex, but they are smaller over a shorter distance, and now the temperature differences that occur will be less. In this example, you see it's only 2 degrees, while if you have no apex seals, it can easily be more than 5 degrees. And of course, to be complete, a few words about optimizing the heating system. And if you have a heating system, you have to take care in the design and implementation to have a homogeneous heat distribution, insulate transport pipes, insulate the sidewalls, and well, even better is to have controlled heating sections per sidewall. So you can measure the temperature around the sidewall locally and control your heating accordingly. And of course, you have to restrict the temperature difference between in and outputs of your pipes. If you have a very slow pump, you can imagine that the temperature difference between the in and the output can be large, which causes also temperature differences around the crop. And then we come to principle 5, and actually that's the main subject for today. That is how temperature differences occur due to our ventilation strategy. Again, we see a cross-section of a greenhouse with the wind blowing from the right, and I already explained that if you open the windows at the lee side, the Venturi effect will cause an air movement from the left to the right. And I think that every grower will recognize this phenomenon, that lee side venting causes an airflow opposite to the wind direction. And when we do the opposite, when we open only the wind side vents, the wind is blowing still from the right, then of course the cold air will enter the greenhouse through the wind side vents and cause an air movement in the same direction as the wind and cause cold spots here and hot spots there. So we conclude that opening the vents only on either the lee side or wind side causes horizontal airflows across the greenhouse. So what is more logical than to open the vents on both sides, both the lee side and the wind side at the same time? Because then the different effects compensate each other, and no dominant or horizontal airflow and resulting temperature differences will occur. And in the second part of this webinar, Hein will discuss in detail how to realize this with the Priva climate control system. And this also works when you have a closed screen. And in the next webinar, we will discuss how this helps a lot to effectively remove moisture during the night, during the period that the screen is closed. Again, you can find more information in the book on the basic principles that can be ordered at the website Plant Empowerment Academy. Well, of course, we expect you to have questions about what I have tried to explain. Feel free to enter these questions in the chat. And after Hein has finished his part, we will collect all your questions and address them as well as possible. Thank you for your attention so far, and well, I now give the floor to Hein.
Good day, all of you. So, as Jan told you, I will tell something about how to implement all the theory, the basic principles of plant empowerment in your climate computer. And Jan Voogd, he spoke about all kinds of influences that affect the greenhouse climate. And we should take these factors into account for a homogeneous greenhouse climate. And when it comes to the use of controls in situation, as Jan told, control greenhouse for me tools helpful to optimize the ventilation and vent control. And how you make make another background to make maybe advantage and vent control is that there will be less harmful influences and fluctuations in humidity, and also an advantage can be, of course, less losses of CO2. So enough stuff to pay attention to vent control. A little bit small, excuse for that, humidity, absolute humidity table, what you see here, the absolute humidities, the temperature, different temperatures, what can be of the air, and here the relative humidities. And why I show you this picture, because in plant empowerment, it's also recommended if it is warm outside and it's humid outside, and the difference between the temperatures and humidity outside the greenhouse is small, to remove humidity. And what is recommended by plant empowerment is to try to increase the difference in temperature inside, outside. In other words, to try to make the temperature in the greenhouse a little bit higher. And because of the activity of the crop, the absolute humidity in the greenhouse will increase. When you make the vents a little bit closer, the crop continues transpiring. Therefore, the absolute humidity will increase, even if the RH doesn't change. And as a result, the difference in absolute humidity in the greenhouse and the absolute humidity outside will increase, so that it is easier to remove the humidity from the greenhouse. Here is an example that demonstrates it. 25 degrees and humidity, relative humidity is 90%, so it's right. Absolute humidity out in the greenhouse is about 20.7 grams per cube. If the measured greenhouse temperature would be, and also about 90%, then you only a small difference between the outside humidity, absolute humidity, and what is really in the air in the greenhouse. When you make the measured greenhouse temperature a little bit higher, or by closing the vents a little bit more, or maybe by using some pipe temperature, but when you make the difference bigger, you will see also that the absolute humidity in the greenhouse increases, and therefore the difference between inside outside also increases, and that's how you can help the crop transpiring, getting rid of humidity. In a situation that there is a small difference in the greenhouse temperature and the outside temperature, like here, the measured greenhouse temperature is 23 degrees, and you can see in the overview M100 also the outside temperatures, 20 degrees, then the difference must be increased. And here I show in another way how you can see it in the greenhouse, in the Priva Connect climate computer. The overview M100, the general overview of the climate, shows the absolute humidity outside, and it shows also the absolute humidity for each compartment. It's like here. And here you see an example with moderate outside temperature and high outside relative humidity, and the difference in absolute humidity in this situation is 2.8 grams per cube. In Priva, you can see in the overview M100.1, the calculated overview, you see the measured greenhouse absolute humidity. So it's the same number as you see in the general overview. You see the outside absolute humidity. That's the same as you see also in the M100. And a nice thing, you can also see it, the difference between inside outside. And that's what I've visualized here. Here, the measured greenhouse temperature is increased to 25 degrees and the same relative humidity. And therefore, the absolute humidity in the greenhouse is also increased. And therefore, now, instead of about 2 so much, now the difference inside-outside humidity has increased to 4.9 grams per cube. So you see the difference is bigger inside-outside, and therefore, through the vents, the same vent opening, you can dissipate more humidity. And here, an example with higher outside temperature and a high outside humidity, absolute humidity. The measured greenhouse temperature is, as always, a little bit higher than outside. And the difference in absolute humidity, here you see the total in the M100.1 overview, is only small. And now I want to continue to the next slide, but I cannot find. Oh, there it is. I have to get used to this way of presentation too, just as Jan had. Now, the measured greenhouse temperature in the greenhouse is increased a little bit to 27 degrees. And we see the difference in absolute humidity inside, outside. Absolute humidity in the greenhouse 23, like here also. Outside 19.6, you can see it also. And you see it is a bigger difference now. Here you can see there is a possibility to adjust by more the heating or the ventilation temperature due to the difference in absolute humidity in the greenhouse and the outside absolute humidity. So you can use this number, this measurement, this calculation to use as an extra influence as here done in the ventilation control. You see, I've allocated the difference between outside and greenhouse absolute humidity. You can do that by double-clicking on this blue hyperlink. And then you can make a set point. And here I've told the computer, okay, if the difference between inside, outside humidity is small, I will increase the ventilation temperature, hoping that the measured greenhouse temperature will increase. And in that way, that there will be more humidity exchange. This is one possibility how you can use the extra influence. The same you could use, for example, to increase pipe temperature or heating temperature, or whatever you want. But this can help you to make an adjustment to your climate control, climate strategy, based on the difference between inside, outside humidity, absolute humidity. And now I have, per accident, copied some slides double. This one also. This one also I discussed. 11. And this one. Excuse for that. And here we can continue. So we had some possibilities to influence controls based on the difference inside, outside absolute humidity. And Jan also spoke in his introduction about the balance between lee side and wind side. Remember, he told in the wind side, when you only use the wind side or only use the lee side, there can be a difference in temperature in the greenhouse. So Now I want to give you some possibilities how you can balance, in fact, the lee side and the wind side vents. One way of balancing the vents of the lee side and the windward side is by means of the P-band settings. And here I've given you an example that the same P-band settings and the same temperature range for minimum and maximum P-band, so the same P-band settings like here, and the same outside temperature range for the P-band to go from the minimum to the maximum P-band will result in the same reaction of lee and wind side when the greenhouse temperature changes. And the minimum P-band, the most aggressive way of venting, is applied when it is relatively warm outside, and the maximum P-band is applied when it's relatively cold outside. But in this example, where I have the same ranges in temperature for both lee and wind side, and the same range in minimum and maximum P-band for both lee and wind side, then the vents will react in the same way when it's becoming warmer. So you can expect more or less the same vent positions for lee and the wind side. With the settings in the example I gave, you see how it reacts in the graph. When it's warm outside, for both sides, a smaller P-band is calculated. In this example, when it's warmer than 15 degrees outside, then the minimum P-band, the most aggressive P-band, will be applied. What you see here as the minimum P-band, a small P-band. And the colder it is, for both lee and wind side, we will have the same increase of P-band, so the same aggressiveness of venting. But when it's colder outside, maybe you would like to have less influence of the wind side. So not closing the wind side, but less influence. And if so, it is possible to set a greater maximum P-band for the wind side, as shown in this example. So here I've changed the maximum P-band for the wind side to 30. The same ranges in outside temperature for now. And that means when it's warm outside, the vents will react in the same way. But when it's becoming colder outside, here you see the outside temperature in the graph. When it's colder outside, you see the lee side has a more aggressive P-band, a smaller P-band, than the wind side. In other words, the vents on the wind side will be used less when it's cold outside compared to the lee side. So making a difference in the maximum P-band for the wind side helps you when it's colder outside to give more priority to the lee side and less priority to the wind side. But still, when the temperature is higher than the calculated ventilation temperature, still both sides will open. So P-band, especially when it's colder, is one possibility to balance between the lee and wind side. Lagging, using the lagging is another way to influence the balance between the leeward and the windward side. The lagging is the difference, in fact, in ventilation temperature for the lee side and for the wind side. In Priva Connect, it is the same ventilation temperature for lee side and the wind side is the case when you set the lagging to 0, as you can see here. In that case, the ventilation temperature of lee and wind side is the same. In other words, if the measured greenhouse temperature exceeds the calculated ventilation temperature, both leeward side and the windward side will open using their own P-band. Here you see that in graph that the ventilation temperature is still the same for both lee and wind side, but you see here the lee side has a more aggressive P-band than the wind side. So they start opening at the same ventilation temperature, but because of a bigger P-band, the vents on the wind side will open less aggressive. Here, I made an adjustment. I've set the lagging to 1. And that means, because I've put in an influence for the wind speed for the lagging, therefore you can see a minimum and a maximum lagging. But for this example, I've put them on the same. The ventilation temperature of the wind side is 1 degree higher at this moment. You can see that always back in the overview M120. You see the calculated ventilation temperature Lee is 20. Because of the lagging, you see here calculated lagging wind is 1, because the minimum and the maximum lagging are the same. And therefore, the calculated ventilation temperature of the wind side is 21 degree. So the difference between the lee side and the wind side ventilation temperature is 1 degree. That's the lagging. And what if I do a thing like this? I make, in this case, for example, depending on the wind speed, I make the ventilation temperature of the wind side a little bit higher or lower. In graph, you see it like this. So if I do nothing extra, you will see at a certain temperature, let's say 20 degrees, the lee side will open with its own P-band. And when it's a little bit warmer, up to 1 degree warmer, then also the wind side will open. But Plant Empowerment told us it would be good to have an opening at the same time of the lee side and the wind side. And when we make a lagging, wind side will start a little bit later. So then we can use a minimum vent position for the wind side as long as the measured greenhouse temperature is just in between the calculated ventilation temperature for the lee side and for the wind side. So how we can make still a small opening of the vents in this temperature range here, so when the wind side for venting is closed, that's what we can do in the following slide I will show you. That you can very carefully start venting on the wind side. In my opinion, an advantage of the use of minimum vents is that you can use this minimum vents, let's say, as a kind of pre-venting. So just before the real vent control takes control, you already start opening the vents a little bit. And the nice thing of that is that the small opening of the vents ensure that the crop can transpire, can evaporate. And when the crop evaporates, the crop will cool the greenhouse, and finally that can help that in total maybe you need a smaller vent position because the crop is more activated. And the nice thing of a smaller vent position is that there will also be less loss of CO2. So I will show you some different options how you can control minimum vents. The first option, often used, is to adjust the minimum vents in a flexible way due to weather conditions. And here is an example where only the humidity part, the humidity increase of the minimum vent position from the lee side is adjusted. It is eliminated over an outside temperature range, which you can see in I120.2, the weather influences, over a temperature range from 11 degrees outside temperature to 7 degrees outside temperature. This part, this increase of the minimum vent is reduced. When you choose here, when you select here humidity, the weather influence only takes effect over this humidity part, this humidity increase. If you also made a setting for humidity for a minimum vent for lee or wind side, that stays not influenced. Well, there are here some different options. You can choose for none, then there will be no influence of the outside temperature to adjust the minimum vents. You can select, as I explained, humidity, then only this humidity increase will be reduced when it's cold outside. And you can also choose for set. In that case, if it is too humid, still this minimum vent is increased, but the set minimum vent will be reduced to 0. And the last option you have is both. And in that case, you can some, sorry, not both, but some. And in that case, if it's becoming colder outside, both the set minimum vent position as well as the extra humidity influence will be eliminated when it's cold outside. The reason why it is possible to adjust minimum vents because of the outside temperature is also agreed by plant empowerment. When it is cold outside, the humidity can be controlled due to condensation on the glass. And in that situation, there's no need for a minimum vent to get rid of humidity. But when it's warmer outside, humidity control needs a larger minimum vent position. And here, per accident, I've used the wrong colors. Of course, this should be the blue one, cold outside, and this the warm outside. And when it's warm outside, you need a bigger minimum vent. When it's cold outside, you need a smaller minimum vent or even no minimum vent when there is enough condensation on the glass. So that's the outside temperature influence on the minimum vents. But what if maybe you made the settings a little bit too aggressive and it's becoming, okay, there is a reduction of the minimum vents due to the outside temperature, but still the greenhouse temperature falls down a little bit. Then there is another option that you can use separately, but also in addition to the possibility I explained before. And that is the influence deviation temperature adjustment minimum vent. That's what you see here highlighted. And the idea is to prevent that the greenhouse temperature drops too much. So when the greenhouse temperature due to the minimum vent position drops down close to the calculated heating temperature, well, then you need to heat and that costs extra money. So that's why we can minimize the minimum vents as soon as the measured greenhouse temperature comes closer and closer to the heating temperature. That's what you can use the deviation temperature adjustment minimum vent for. And here you see when it's really close to the heating temperature, a small difference to the heating temperature, you see the minimum vents are adjusted according to the table, the settings table, what is here displayed graphically. Another nice possibility, which must be set up by the dealer, but it can be a very nice one, because the former possibility, then it is the minimum vent is related to the heating temperature. And that can happen when you adjust your heating temperature, and there's no adjustment needed for the ventilation temperature, that influences the minimum vent. And that's the reason that I'm fond of the possibility I'm going to explain now. It is possible to allocate an extra influence, so-called extra influence to the minimum vent position. And that's what you can do on lee side, on wind side, or on both sides. This extra influence can be allocated to the temperature difference, which you can see in the overview M120, which shows the temperature difference of the greenhouse between the calculated ventilation temperature minus the measured greenhouse temperature. And this allocation to that extra influence, it is not in the list when you click on this hyperlink, so the dealer must set it up for you, but it can be very helpful. In the example, a minimum vent for the lee side is applied from the moment that the measured greenhouse temperature is less than 0.7 degrees below the calculated ventilation temperature. I try to show it you here. So the set points here are difference of 0.7, no problem, but it becomes closer, so then it stays closed. But when the greenhouse temperature rises closer to the ventilation temperature, but still didn't reach the ventilation temperature, I'm going to start opening the vents already a little bit, the kind of pre-venting. And that's what you see here. According to this settings table, you see now the temperature is like here, the greenhouse temperature. I try to visualize it here. When the temperature is still below the measured temperature is still below the calculated ventilation temperature, but just a little bit below, we start opening the vents a little bit, pre-venting in a very controlled way so that we can activate the crop. And when it's becoming a little bit warmer, you see the vents are on the maximum, so let's say about 3%. And that's what we can end with, because then ventilation control can take it over. So this is a nice way how you can start venting very precisely and activate the crop, try to get rid of humidity, make the crop start transpiring, and keep the CO2 in the greenhouse, because you are only limited venting. And then there's another option, which I will not discuss in detail, but it will be in the Priva Academy very soon. Some growers prefer to use a so-called negative lagging. And the negative lagging, when you put it like here, so the lagging, not the positive numbers, but negative numbers, that means that the calculated ventilation temperature, which you see in I120, then it will not start opening the lee side, but it will start opening the wind side. So when you put in the negative lagging, instead of this way of venting, wind is in this direction, this would happen at the positive lagging, so the lee side would open more than the wind side. When you put in a negative lagging, the wind side opens more and at a lower greenhouse temperature, and the lee side will follow. It would take too much time for today to explain you in detail, but again, if you need some more explanation about that, because you're interested in doing it that way around, soon there will be the explanation in the Priva Academy. Henry, this is for me the part, so thank you for your attention.
Thank you, Hein. Thank you, Jan. Just a quick review, everyone. So next week, same time, so on September 24th, part 2 of 4 of the series. We hope that you could can join us for all 4 sessions. If you're not able to join one, no problem. We are recording them. So for those who missed today's, they can review the first session on the Academy shortly. And one more point here, just for those of you who do not have the Plant Empowerment book, of course, you can go to the plantempowerment.academy website, and that's where you can order the book online. So thank you again for joining us today. It's always a pleasure to have Jan and Hein present and session.